today we will see the circuit reduction and some other topics along with these important topics regarding the star delta connection, star to delta and delta to star, and we'll solve some problems. So first we'll go through the circuit reduction. So here you can observe the circuit. So there is a source voltage of 5 volts and there are totally 7 resistors. So we can replace this resistance with a single resistor, that is R equivalent, and we have to find that value. So first we will start from here and see R6 and R7 both are in series. So in our previous lectures we have observed if they are in series we can simply add, and if they are in parallel we can take it as R1 into R2 by R1 plus R2. So with these techniques we'll let us solve this. Let us simplify this circuit. So R6 and R7 are in series and we'll simply add. So R6 is 2 ohms and R7 is 2 ohms. So 2 plus 2, so that is 4 ohms. So we'll replace this R6 and R7 with a single 4 ohm resistor. So that is, so these two are in series. So now we will add these two things and we will simply replace. Here you can observe. So we have replaced that R6 and R7 with a single resistance, that is 4 ohm resistance. So now this newly formed 4 ohms resistor is in parallel with R5, and this R5 is in parallel with this newly formed 4 ohm resistor. So that means with simple formula R1 R2 by R1 plus R2. Here we can find this 4 ohm as R1 and this 4 ohm as R2. So that is 4 into 4 by 4 plus 4. That is 16 by 8. You will get 2 ohms. So that means we are going to replace this R5 4 ohms and this 4 ohms, these two resistance with a single resistance, that is 2 ohm resistance. Okay, and so here we have replaced. So this newly formed 2 ohm resistor is in series with 10 ohm resistor. So we can simply, if they are in series, we can simply add. So we can replace with a single resistance instead of this 10 ohm and 2 ohm with a simple resistance, that is 12 ohm resistance. So that's the same thing we have done here. And this is the new circuit with the newly formed 12 ohm resistor instead of this 10 ohm and 2 ohm resistance. So again, if you observe here, so this R2 and R3 both are in series. So again, we can simply add. So that means 8 plus 4, that is 12. So we have replaced this 4 ohm resistance and 8 ohm resistance with a single resistance, that is 12 ohm resistance. So that is 12 ohm. So again this 12 ohm is in parallel with this 12 ohm. So these two are in parallel. So simply we have to write it as 12 into 12 by 12 plus 12. So that is, we will get 144 by 24. So the result is 6 ohm. So that means we will remove this 12 ohm and 12 ohm and simply we will replace these two 12 ohms with a single resistance, that is 6 ohm resistance. So this 6 ohm again, the newly formed 6 ohm again is in series with the 4. Again, if they are in series, again we have to add. So that is 10 ohm resistance. So that means, so now the R equivalent is 10 ohm resistance. That means 5 volts in series with a 10 ohm resistance. Okay. So if you see, if you observe, this is the initial circuit, and we can simply reduce this circuit into a simple circuit with the help of this circuit reduction technique. So now we will see what is the star connection and what is the delta connection. Okay, so we can also call this the star connection as the Y connection, or Y. See, or otherwise in reverse we can write like this also. We'll call it as the Y connection. So generally it is a T network. It is a T network. So that means ground line, we will remove it and we will consider. That means there will be a one resistor, one element, 3 elements. So connected with a common point. There one end is connected to a common point. So this T network, we will call it as a Y or a star connection. See, you can observe here. So if you observe here, this is the actual network. So this we can represent like this. So if you remove this line, bottom line, so it will be in the shape of the exactly T. So that means we can reform like this, which is looking like a star or inverse star, inverse Y, Y or a star. So that's why we are calling it as the star connection. So now this is the star connection and this is the delta connection. So according to the necessity in the circuit, we will change the star connection to delta and delta connection to the star connection. Okay. So now we will see how we are going to do it. So first we will take this example. So this is the delta network and this is the star network. So now how I will change this star into delta. So here in the star we are having RA, RB and RC, and in the star we are having R1, R2 and R3. So we have to change this RA, RB and RC into delta form in the resistance R1, R2 and R3. So even though here there are 3 resistances and here also there are 3 resistances, but the values will be varying when you transform. So for that we are going to use this formula. So R1, now I want R1. So always you have to remember, in the delta the numerator will be common and in the star the denominator will be common. So first thing is I want R1. So numerator is common. So RA, RB, RB, RC, RC, RA, that is the numerator, into divided by, that is RB. So R1. If you observe in this table, so this R1 is exactly opposite to the point B, that is which is connected, that means it is connected to resistor B or B. So I will write it as R1. So numerator is common and for the denominator I will see the R1 is opposite to the point B. So this is the easy way to remember the formula. Okay. So that means whenever it is connected to point B, that means so it is connected to the resistor RB. The resistor which is connected to the B is RB. So I will write as RB. Similarly, we will also write the R2. So numerator RA, RB, RB, RC, RC, RA by, so R2. So R2 is exactly opposite to C. That means it is point C. It is opposite to the point C. That means it is connected to C. So I will write as in the numerator as the RC. And R3. Numerator is same, RA, RB, RB, RC, RC, RA, and R3. So if you observe here, the R3 is opposite to point A. So that means RA is connected to the point A. So I will write it as RA. So this is how you can easily remember these formulas. And now we will see from delta to star. So here again, numerator will be common. So I want RA. So here R1, R2 and R3 are forming a delta, and RA, RB and RC are forming the star. So RA is, so I want now RA. So if you observe this RA, so for example, I will think that, so here if you observe here to the point A, which are connected in the delta. So R1 and R2 are connected. So I will write it as R1 R2 by numerator R1 plus R2 plus R3. So I want RA. So here I observe the point A. So that is for the point A, R1 and R2 are connected. So I will write it as R1 R2 by R1 plus R2 plus R3. And point R3. So simply you can, R3 also the denominator is common. But here in the star we have to observe to which point. So what are the resistors connected? So that means to the point B, R2 and R3 are connected. So R2, R3 by R1 plus R2 plus R. And similarly RC. So denominator is common, that is R1 plus R2 plus R3. And to the point C, R1 and R3 are connected. So I will write as R1, R3 by denominator R1 plus R2 plus R3. So this is the simple way to find the, remember the formulas. And now we will see, this is the circuit. So we have to find the R equivalent, means there are two delta connections are there internally in this circuit, and we have to convert one thing into a star to solve for the circuit direction, to find the circuit direction. So what I will do? So the points are A, B, C, A, B, C. So this delta I want to form. So point A. Okay, so that means I want this RA, RB and RC. So that means the resistors connected to these points. Okay, so RA. So at this point I will see what are the resistors connected in the delta. So 10 into 5 by all the three resistances, that is 10 plus 5. So that is equal to 50 by 25, that is equal to 2. So that means this value I will get 2. And I will come to point B. So that is, for the point B, what are the resistors connected? So I want RB. So 10. This is also 10 into 5 by 10 plus 5. Because in the numerator we will add all the resistors. So this is also T by 25, that is equal to 2. And again I will come to the point C here. So that means the value here will be 2 again. And I will come to the point C. So again, for the point C, 10 into 10 by 10 plus 5, that is equal to 100 by 25, that is equal to 4. So here I have to write the value as 4 ohm resistor. Okay, so I have simplified it by using the formulas delta to star. Similarly, we can find for star to delta. But here, for this circuit direction, we needed to convert this delta into star. So the same thing. So that is 10 into, so for point A, 10 into 5 by 10 plus 10 plus 5. And RB, 10 into 5 by 10 plus 10 plus 5. And RC, 10 into 10 by 10 plus 10 plus 5. So that is equal to 4 you will get. And so I have replaced it here. Okay. So that is 2 ohms and 4 ohms and 2 ohms. Okay. Okay. So if you simplify this, you will get the equivalent circuit as the, that means 9 plus 2 plus, so 8 plus 4, that is 12 parallel to 8. So that is 12 into 8 by 12 plus 8. So if you simplify, you will get exactly 15 ohms as the answer. So this is how we are able to find the equivalent resistance in this thing. Okay, next we will see another problem. That is, so this is also, this is a pi network, and if you remove this thing, and we have to convert this into star. So here also again, so we have to imagine the points A, B, okay, according to this way, C, and this is the B, A, B, C. So now RA, so 5 into 10 by 5 plus 3 plus 10, if you simplify, you get 2.77, and RB, so 10 into 3 by 5 plus 3 plus 10, and RC, 5 into 3 by 5 plus 3 plus 10. So this is how we are going to convert this delta into star. Now we will see the source transformation, and which cases we can transfer the current source into voltage source and voltage source into current source. So if you find any network, so voltage, there is a voltage and there is a resistance in series with the voltage. So now I can transform this as a current source in parallel with the resistance. Okay. Or if I find the current source and parallel with the resistance, I can transform a voltage and series with a resistance. And two voltages, V1 and V2, are in series. I can simply add and I can replace with a single voltage source, that is V. And similarly, two current sources are in parallel. I can simply add and replace with a single resistance, single current source, that is I is equal to I1 plus I2. And similarly, if there is a circuit where the voltage source and the resistance is in parallel, if I remove this, also there will not be any change. So I will simply write it as only what I can remove this resistance and I can transform. Similarly, if there is a current source and only a resistance, I can, even though I can remove one, I can transform. So next we will see what is the mesh analysis and what are the yesterday also we have seen what is KVL and KCL, and we'll see the. So there is a circuit. First you will find the loops or closure paths. How many closure paths or how many mesh are there? So that is V1 and V2. Mesh 1, mesh 2. So 1 kilo ohm, 1 kilo ohm, and 1 kilo ohm. So there are two mesh. So I have to imagine two currents, I1 and I2. And now how I am going to, so I have imagined both the currents in the clockwise direction. So I will start from here and I will, so here there is negative sign, I will write minus V1 and R1 and the current. So I1 R1, and this R3 is common for both the mesh or both the loops. So since I am writing about the first loop, so I will write as I1 minus I2. If I am writing for the second loop, I will write as I2 minus I1. So that is I1 minus I2 into R3 equal to 0. So this is how we have to form the equation. And if there are values, we can solve the equations. So I am coming to the second loop. So here again I2 R2. So I2 R2. Here I am able to see, if I come in this clockwise direction, I am able to see the positive sign. So I will write as plus V2. And coming to the R3, which is common for both the loops. So I2 minus I1 into R3. So this is how we are going to make the mesh loop equations. Okay, for the loop 1, for the loop 2. So if there are two loops, we are getting two equations. If there are three loops, we will get three equations. And we'll see here, we'll observe. So this is the circuit where you are having a source. So we are having two loops here. Okay. So there is a voltage source in the first loop and there is a current source in the second. So generally, if there is voltage source, the second loop also you have to form the equation. So here there is current source in the second loop. So first we will go for the first loop. So here the clockwise direction again and minus 10. So clockwise direction, if I observe, minus is there, I will get minus 10 plus 4 I1. So 4, and we have to imagine the current in the first loop as the I1 and the second loop as the I2. So that is 4 I1 plus 6 into, we are having, this is common for both the loops. So I have written as 6 into I1 minus I2 is equal to 0. So that is the case of the first mesh, first equation. In second loop, if I go simply, I will observe. So there is already current. So I want the current. So that is current is 5 amperes. So there is no need for writing the equation because he has directly given the current value. And we will see what the for this circuit, we will observe again how we can solve. So first we have to imagine the loop currents. So for the first circuit, I1, and for the second circuit, I2. I1 and I2. So first So 3 I1 plus 5 I1 minus I2, because 5 is common for both the loops. So I1 minus I2 plus 6 I1 minus. So if I go this direction, I have to observe the minus sign. So minus 50, that is equal to 0. Okay. Second case. So in this case, I have assumed both are in clockwise direction. So there are different, either we can assume both are clockwise, both are anti-clockwise, or you can go by this sign. Okay, anyway, but answer should be same. So here 2I2, since this is the second loop, the current will be I2. 2I2 plus 8I2 plus 5I2 minus I1, because I am referring the second loop. So I will write as I2 minus I1. And if I coming in the clockwise direction, I can see the positive sign in the 25 volts. So plus 25, that is equal to 0. So all of you. So first I have assumed the currents I1, I2. So 3I1 plus 5. So since this is the first loop, 5I1 minus I2. Okay, I am referring to the first loop. Plus 6I1. So current in the first loop is I1. Current in the second loop is I2. Plus 6I1. So if I go in this direction, clockwise direction, I can observe the minus sign. So I will write as minus 50. And here also 2I1 clockwise direction. The current in the second loop is I2. So 2I2. And here I can observe the positive sign plus 25. The voltage is 25 plus 8I2, because the current in the second loop is I2. So 8I2. And 5 is common for both the loops. So I am referring to the second loop. So I will write as I2 minus I1, that is equal to 0. So if you simplify, so the first equation I got 14I1 minus 5I2 is equal to 50. And the second equation minus 5I1 plus 15I2 is equal to 25. So since there are two loops, we will get two equations. So we are going to solve the two equations. So I will write it as 14I1 minus 5I2 is equal to, after simplification, that is equal to 50 as the equation 1. Minus 5I1 plus 15I2 is equal to minus 25 as the second equation. So now I have to solve this, and at least I have to find one value, current value. So, I have multiplied the equation 2 by 3. I have multiplied the equation 1 by 3. So that means, that is 42I1 minus 15I2 is equal to 150. So the second equation is same. So here 15I2 and plus 15I2. So both will be cancelled, and 42 minus 5I1, that is equal to 37I1 is equal to 125. 150 minus 25, that is equal to 125. So now I got the value of I1. So I1 is equal to 125 by 37, that is equal to 3.37 amperes. I got. So I will substitute in the one of these equations this value, I1 value, and I will find the value of I2. So I will get the I2 value as minus 0.541. So this is how we are going to find the values, I1 and I2 values. So again, so in the circuit reduction, so first I have started from this right side, and these two are in series. Simply I have added and replaced with the new value. So again, this 4 and this 4 are in parallel. So R1 into R2 by R1 plus R2. So replace with the value of 2, and 10 and 2 are in series. So that is replaced with 12. Okay, 12, and these 12 and 12 are in parallel. So 12 into 12 by 12 plus 12. So replaced with the value of 6, and 4 and 6 are in series. So replaced with the value of 10. And finally, this big circuit I have simplified into a small circuit, and I have found what is the R equivalent also. So star connection and delta connections are the common type of connection we will find in this circuit, and according to the necessity we will convert the star into delta or delta into star with the help of a formulas. So both the cases we will be having 3 resistances only, but the values will be varying. So this is the T network. So because it is looking like a T, that means there are 3 elements, 3 resistors are there. So if this is the case, the circuit is like this. Okay. So if I will remove this bottom line, and if I add these things, it will be, so it is a pi network. If I add these things, it will be looking like a delta. So that is called as a pi network. So T network we will be calling as star, and pi network we will be calling as a delta network. So we can convert star to delta and delta to star, and there are formulas for that conversion, and the easy method is that, so here from star to delta, so the numerator will be common, and delta to star, here the denominator will be common. And with that, so here we want to find actually finally R equivalent, and so for that purpose we have converted this upper delta into star, and we are able to solve the problem with the help of the delta to star formula. So okay, and after forming like this, we will simply add the resistors in series, and these two values we got, and that is 8 into 12 by 12 into 8. So the resultant value plus that will be 4 ohms. So finally this 9 plus 2 11, here we will get the 4 ohms, and that will be 15 ohms. So this is the pi network. So this is looking like a pi network. We will convert, that means it is a delta network. So we have converted into star. We have to convert into star. So that is delta. So we have assumed this as A, B and C. So for the point A, 10 into 5 by 5 plus 3 plus 10. For the point B, 10 into 3 by 5 plus 3 plus 10. And point C, 5 into 3 by 5 plus 3 plus 10. And source transformation, that is voltage source in series with the resistances can be transferred into a current source in parallel with the resistance. And 2 voltage sources are in series, it can be replaced with a single voltage source by adding these 2 voltage sources. And 2 current sources in parallel can be replaced by a single current source simply by adding those previous two current sources. So if the voltage source is in the parallel, the resistor is in parallel to the voltage source, there is no change, so we can remove this resistance. If the resistor is in series with the current source, there will be no change, so we can remove this resistance and we can and simply we have seen. So if there are two loops, for two loops we have assumed two currents and we have assumed the directions. For the first loop we will assume as I1 and for the second loop we will assume as the I2. And according to this we have written the equation. So see here, so R1, this clockwise direction R1 plus R3 is common to I1 and I2, so I am referring to the first network, so I will write as R3 into I1 minus I2. So in this direction, when I can observe here as negative sign, I will write as minus V1. So the source in the first loop. So similarly, if I go in the second loop, I can observe plus V2. So plus V2 and R3. So I am referring to the second loop. So I will write as I2 minus I1 and R3 into I2. So done this technique. And this is the different case. If there is a current source in the second loop, we can directly write the current value. And this is the case where we are having both the voltage sources, and we have written the equation for the first loop. And we have simplified and we have found what are the values of I1 and I2. Thank you for listening.
Like, share and subscribe. Hit the bell icon for more updates.